So the first of two examples I posted with the class notes. I thought this would be really fun and kind of interesting, which is how much energy is transmitted in a wave. When I went to work through this problem, turns out a water wave, particularly a fast-moving ocean water wave, they can't really be modeled as simple strings. So this turns out to be super complicated to do. We'd have to talk to oceanography to get a solution for this one. So I'm going to say let's pass on this example and go straight to the next example. So our next example probably looks a little bit familiar. A 1 kilogram mass is hung from a 60 centimeter steel wire which is attached to a support. If waves with frequency of 50 hertz and amplitude of 1 meter are generated, how much power is delivered through the wire? So this is the example we did in the previous example video. We found that when we plucked the wire, it led us to find that the mass of the wire was 4.19 grams. We also found that the speed of those waves was 37.5 meters per second. So let's go through this problem, make a list of the things that we know, and we'll include things that we learned from this problem. So let's start with a picture. There's the support. There's the wire. There's the mass on the wire. So this is our length, 60 centimeters. This is our mass M, where mass M is 1 kilogram. For our wire, that was little m, 4.19 grams. We know that our wave is generated with a frequency of 50 hertz. We know that the amplitude is 1 millimeter. And we also know that the speed of the wave, we found on a previous slide, was 37.5 meters per second. Okay, and what we're asked to find is how much power is delivered through that wire. So what's the power of that wave on the wire? Let's write down our equation for power. Power equals 1/2 times mu times A times omega squared times V. What do we know here, or what can we figure out? Mu is our mass per unit length of the wire. We did find that in the previous slide, but we can just put in those numbers again if we wish. So the mass is 4.19 times 10 to the minus 3 kilograms, divided by 60 centimeters, or 0.6 meters. The mass per unit length of that wire is 6.98 times 10 to the minus 3 kilograms per meter. Okay, and that was something we found in the previous slide. Omega, that's angular frequency, that's 2 pi f. So 2 pi times 50 hertz equals 314 radians per second. And what else do we need? V, we know it's 37.5, so we can put our numbers into our power equation and we can calculate the power of that wave. So 1/2 times mu times the amplitude, make sure you're putting stuff in meters, times omega squared times the wave speed, 37.5. Put all that through the calculator, we get 1.29 times 10 to the minus 2 watts. Okay, so there's our traveling waves. We only have a little bit left to do in this chapter, and then we'll be able to finish it up.